Let's take a look at section 5.3, which is on a really important topic in calculus. This is kind of an exciting topic. Maybe exciting is a strong word, I'm not sure, but it's a topic we definitely will use over and over again the rest of the course, and it's kind of a cornerstone of what we do in calculus. And that's called the fundamental theorem of calculus. So it's kind of broken into two parts here, and every book does it a little bit differently, but this is how our book does it, where it's like a part one and a part two. And part one says if f is continuous at every point in the interval from a to b, in capital F is the antiderivative of f. So we're talking about the antiderivatives, those antiderivative rules we learned back at the end of chapter 4. Then the integral from a to b of the definite integral, I should say, of f of x with respect to x can be evaluated by finding the antiderivative and evaluating it at b minus the antiderivative evaluated at a. And that's the fundamental theorem. So when we've been evaluating these definite integrals, we've been estimating using Riemann sums or using properties that they gave us and known information or geometry or something like that. Now we can actually calculate exact areas under an integral using the antiderivative rules we learned back in 4.9. So let's do a couple of examples. Number one, evaluate the integral of the function x squared minus 3 from 1 to 2. So what this theorem says is I'm going to find the antiderivative for x squared minus 3, and that's going to be x to the third over 3 minus 3x. And then I always write this using kind of a bar here, and I say from 1 to 2. So this theorem says I'm going to evaluate this antiderivative at the upper limit, which is 2 to start off. So I've got, and I'm going to use a bracket here to kind of separate everything. I've got 2 to the third over 3 minus 3 times 2. And then we're going to minus the integral of 1 to the third over 3 minus 3 times 1. And then let's see what that gives me. 2 to the third, of course, is 8. So I have 8 thirds minus 6. And then minus 1/3 minus 3. So I'm going to get a common denominator. 6 is, of course, 18 over 3. So 8 thirds minus 18 thirds gives me negative 10 thirds. And then minus over here, 3 would be 9 over 3. So 1/3 minus 9 thirds would give me negative 8 thirds. So that becomes negative 10 thirds plus 8 thirds, which gives me negative 2 thirds. Let me write my final answer up here. And let's take a look. Because this is negative, that tells me that the majority of the graph over this interval from 1 to 2 would be below the x-axis. So let's take a look at what this would be in Desmos. So I've got the definite integral calculator pulled up in Desmos so you can see what we have. We have the function x squared minus 3, which is a parabola, and they wanted us to evaluate it from 1 to 2. So you can see below the x-axis over here from 1 until this x-intercept right here, which would be at the square root of 3, we've got the area that's shaded in blue. It looks like a triangle, but don't be fooled. It's not a triangle because of the curve in the parabola. So this is a region down here, and then from that point of that x-intercept to 2, we've got another region. Again, it looks like a triangle, but it is not because of the curved function. So when you put these together and you calculate the definite integral using the theorem, we get negative, Desmos gets negative 0.6 repeating, which of course is the same as negative 2/3. Let's do another one, the integral of secant squared x from 0 to pi over 4. So we know the antiderivative for secant squared, that would be tangent. So that would be tangent x from 0 to pi over 4. And that would be tangent of pi over 4 minus tangent of 0. So tangent of pi over 4 is 1, and then tangent of 0 is 0. So that would just be 1. So my area under that curve would be of secant squared would be 1. One thing I did not mention, I just thought about, and I should have mentioned this sooner. You'll notice that with both of these, I did not include the plus c. So when you have a definite integral and you're applying the fundamental theorem to evaluate it, you do not need to include the plus c, because when you take the difference between these two, the c, whatever it would have been, would cancel out or zero out anyway. Let me show you as an example with this tangent function. Had I made the antiderivative tan x plus c, then from 0 to pi over 4, I would have said tan of pi over 4 plus c minus tan of 0 plus c, think about in parentheses, and you can notice that those c's would have zeroed out anyway. So when you're doing a definite integral, it is not necessary to write the plus c. You really don't have to do that. The only time you have to do that is if you're doing an antiderivative or solving a differential equation. But this is it. This is what we're going to apply to evaluate these definite integrals from now on, unless the directions tell you otherwise. Let's try the next part. The second part of the fundamental theorem is a way to kind of tie together the integration rules that we're using and the derivative rules that we've previously learned. You can kind of think of differentiation and integration as sort of inverse operations. Essentially, that's what they are. And that's what this theorem does. It kind of ties those ideas together. So it says, if f is a continuous function at every point in the interval a to b, then the area function would be the integral of f from a to x, where a ranges from, or x rather ranges from a to b. This is called the area function. This is also called an accumulation function. And all this means is that if we were to integrate f from a to whatever x value we're talking about, we cover the area of underneath the curve. Let me just give you a quick image of what this might look like. Let's say f of x is equal to x squared. So if we graphed that in just the first quadrant there, and we looked at the area, let's say we could say it's the integral from 0 to x. And they're using t. T is called a dummy variable because the t is not what's important. The t doesn't matter. I'm using x as the upper limit, so that's the variable in my accumulation function itself. Don't worry about the variables. That's not the important thing. But what this would mean is if I said, okay, what is a to 2, for example, that would be the integral from 0 to 2 of the function t squared dt. So basically it would just be the area under the curve from 0 to 2. And if I changed it and I said, what is a of 3? You would tell me it's the integral from 0 to 3 of that function, and you would just extend this out to 3 and cover a little bit more of the area under the curve until you get to 3, and so forth. So that's called an accumulation function, and we'll look at that a little bit more in class. But let's keep going. What's the rest of this theorem say? So a of x is defined as this area or this accumulation function. It will also be continuous on the interval from a to b and differentiable. Equivalently, so here's sort of the heart of the part of this theorem. The derivative, a prime of x, or you could note that as d dx of this integral, would just be f of x. And let's talk about for a moment why this works. Forget the derivative part for just a minute. Don't write that, but just forget the derivative part for just a minute. If I just gave you this, one way to think about this integral would be the antiderivative, f evaluated at the upper limit, minus the antiderivative f evaluated at the lower limit. Now, think about, let's go back and include the d dx, the derivative. What is the derivative of this expression? Well, the derivative of capital F of x, wouldn't that just be little f of x? And then if f of a would be a constant, this part, so the derivative of that would be 0. So you don't have to worry about that. So what you're saying is a prime of x, or the derivative of this integral, is just f of x. And that's what this theorem tells you. This is more complicated than maybe it seems at first, the explanation. Let's do a couple quick examples, and then we'll do this in class, as we always do. So we'll see how this applies. But let's just do a couple quick examples. Part A says evaluate the expression, so they want d dx, the derivative of this expression, sine squared of t is the function, from 1 to x. So what this part of the theorem says is it's literally just going to be f of x. So f is the sine squared function, so it's going to be sine squared of x. And that's it. That's all there is to it. As long as this lower limit is a constant, just like a, doesn't matter what it just has to be a constant, because you saw how it zeroed out when I actually walked through it and took the derivative. That's going to work for your derivative of that area function. Let's do another example here. So they want d dx of the integral from x to 5 of that expression. Now, one thing to notice is that the constant is not on the bottom. The constant's on the top. So in order for this theorem to apply, the constant has to be on the bottom. Well, lucky for us, we have a property that we learned in 5.2 that says we can swap these limits of integration by making this negative. So this can be rewritten as d dx of the negative, let me put a bracket around this, the negative of the integral from 5 to x of that same function, t squared plus 1 dt. Oops, sorry about that. Let me slide my screen over just a smidge. There we go. And now it's in the format that I need for me to apply this theorem. It's the integral from a constant to x. So the derivative of this expression is going to be negative square root of just x squared plus 1. And that's it. And that's going to be the derivative of that integral expression. And that's the second fundamental theorem. So bring your notes with you and we will work on this and apply some of this in class tomorrow.